continuing on with our value noise implementation here in part two. Lee is going to, well, finish up the 2D version of it. Lee?
Right, we're actually going to implement the value noise part of it. What we've done right now is just box blurred our noise that we're sampling from our hash 2D. We haven't even really done the value noise part of it yet. So let's go ahead and start coding that out. We're going to need a public static. This is going to return a float. We're going to call it value. And we're going to take in a float x and a float y. And more squiggly braces so we can do stuff inside of them. Now, the first part I want to do is create a couple of variables that are going to help define our unit square for our noise. So we're going to take, not utils because I coded it directly inside of here. We're going to take our floor that we've defined inside of noise, and we're going to pass x into it, and we're going to save that in a variable called I. We're going to do the same thing with a variable called j, but this will take the floor, not float, floor of y.
Wow.
That was awesome.
Yes, it was.
Okay, so now after many keys of typing and erasing, we've gotten the floor of both x and y. Now, if you remember when I was explaining how floor works, we're just trying to take the lowest value of our x or whatever we pass in. So if it's a positive number, we're going to get a truncated version. So if we have 4.5, we end up with 4. If we end up with a negative number like negative 4.5, instead of it getting truncated to negative 4, it will truncate it to negative 4 and then subtract another whole number from it, which leaves us with negative 5. And what we're doing is we're trying to get the lower bounds of our unit square. And then we're going to take that and we're going to get our upper limits of our unit square. That's what these next values are going to hold. So we're going to get our x lower bounds. That is going to be equal to I, which is the floor of x. We're going to get the upper bounds, so this will be, well, not bar. I am really not having a good day with the keyboard.
Told you should have had some coffee. Continue.
Yeah. So we've got our high bounds of x, which is going to be I.
Do you want to go with high or upper? Nothing.
Well, I'm trying to keep these the naming convention kind of consistent with what are in the papers. So if we go back over here, because I don't want to deviate too much from what's in the source documentation that I've been using. So if people want to go back and forth between them, they're not completely confused. But I am making some changes here and there. So if I can find where it is. And no, I'm completely changing it.
I thought so.
They're using V1, but they're using fractional X. I've read so many papers on noise. Some of them come from some sources, come from different sources. So this would be X low, X high.
Okay.
And we do the same thing with Y. So we've got Y low, which is going to be equal to J. Wow. Maybe I might have to go get some coffee after this. So then we'll get YH is going to be J plus 1. This is just defining the corners of our unit square. Now we're going to do a noise sample, and this is going to be, let's use low. I use 0, but I'll just try to keep it a little bit more consistent. So smooth noise, we're going to sample at XL, so our X low, by our Y low. The same line is going to be duplicated 3 more times. but our noise sample is going to be at x of high and low, and then low by high, and then high by high. That's almost as good as Nelson's this and that.
Yeah.
So x, the high value of x and the low value of y, low value of x, the high value of y, high value of x, and the high value of y. Now, basically, these are just defining each of the corners of what we're going to be using for our sample. Now, we also are going to define a var called u. Now, we've taken x, which is a float, and we've run it through a floor function to get the lower part of it, which comes out as I, but we want to get the fractional part of it because we need to figure out inside of our unit square exactly where x and y live. So while this is defining the 4 points of our unit square, we need to know the exact center, which is what we're trying to interpolate to. So we're going to take our x, which is our float, and we're going to subtract I, which is an integer, from it, which really leaves just the fractional part of that number. So we'll take u will equal x minus y. We'll define v as y minus j, which is going to leave the fractional part of y because j is the floor of y. Now we need to do some blurbs. So we're going to take nx low is, actually this is going to be ny low. So ny low is going to equal our mathf.lerp, and Alt enter. So that will add Unity Engine into our using statements. We're going to take every place where y is low. So this is going to be our n low low and to our nhl. And we're going to lerp it by u, which is our fractional part of our x. So we're taking we're going to be looking at our, or in this case, our where y is low. On both cases, we're going to go from x low to x high by the fractional part of x, which is defined by u. Then we're going to do the same thing again with our, let's do ny high equals math dot lerp, and we're going to this time look at where n is low to y of high by n of high by high by the amount u. And if I were to, I'm trying to think, let's go to Photoshop real quick. Try to make this easy. So if I go File, let's do New, and let's do 800 by, we're at 1280 by 800, right?
Yes.
All right. So 768 should fit just fine. Yeah, there we go. All right, so if I fill that with white in our background, and let's go ahead and make a nice little unit square. Stroke that with 1 pixel black. Nah, still too faint. Stroke. There we go. All right. So if this is our unit square, and if I take text, because I'm definitely not going to try to code this up with, or write this out with a mouse. So let's go to 24. So where this would be our sample point for n low low, and this one would be NHL for x being high and low. This one would be NLH, and this one is going to be NHH. What we're doing with these first two lerp operations is, if I go and get my line tool, we are defining where U is going to be. So U is our fractional part, and we're basically going and saying that the distance between here and here is the value U. And then we're going to do the same thing again, where we're finding a point here, and this point would be our V. I'm not even going to attempt to draw arrows, so. So what we're doing is trying to figure out where our sample point is, which would be at this point right here. And
Let's throw a new layer on there, and
yeah, can't do that in text.
hey, it's the time, and it's a normal time for us during the day.
Yeah, it's
which
kind
is
of
why
weird
your
how
fingers are not yet awake.
Yeah. All right. So, but if we're trying to find this point right here, then what we're doing is by taking the floor, this will make it a little bit easier to understand, and overall, by taking the floor of our position, we're trying to find this point in space. So if I were to take text, and just to keep it consistent with what I've been saying is, if this was 4.5 in X by negative 4.5 in Y, then what we end up with is NLL ends up being a point that is 4 by negative 5. And then we're calculating our other unit square points based off of this number. So NLH would be 4 by negative 4. NHL over here is going to be 5 by negative 5. And NHH is going to be 5 by negative 4. But we still need to figure out what color or what shade of gray this point is going to be. So by taking our floor of X, subtracting I from it, we get U. By taking our Y, subtracting J from it, we get our V, which is our fractional part here. So right now, the two lerps that we've done is lerping between NLL and NHL by U, which gives us this point in color based off of our noise samples. And the next one we're going to be doing is calculating our V here to get our contribution on this part, which gives us our color right here. So hopefully that clarifies what's going on a little bit easier.
Okay.
So now if we jump back over to this icon, we're going to take var n by x by y. So this will be math.f.lerp, and we're going to take our output from nyl and our output from nyh, and we're going to lerp it by v. That's basically taking our two numbers and then lerping those together so we can get our final number. And then we're going to return nxy. Now, we're going to multiply this by 2, and we're going to subtract 1f from it. The reason why is this calculation is going to return a number that is going to be in the domain of -1 to 1. And we want our noise to come back as a value of 0 to 1 in our calculations. If you wanted, because we're using this in, for color, if we wanted it to be noise that was additive or subtractive, we could remove this out and just return a -1 to +1 value. And then if you wanted to force it to a different domain, you'd have to handle it separately. But for now, I'm going to leave it as just the 0 to 1 range to correspond with our example. So if I go back into our game manager, and instead of using our smooth noise now, if I define n as equal noise.value, and I give it our x and our y, and build it, hopefully, if everything works right, we should get some value noise. Now, if I go back here and I hit play, I'm pretty sure I hit play. There we go. Now we start getting some different noise. Now we're getting some black in here, so we're definitely not getting completely 0 to 1. Or a lot of it is set to negative. Let me
Hang on. I don't think it actually caught your stop.
Yeah.
Yeah, you just got to give it a minute because this operation takes 6 seconds.
6 seconds, almost 7 seconds.
Yeah.
So we're going to have to fix that as well.
Yeah, that's horrible.
Yeah. Which is kind of why I said this is not something we want to do in real time. All right, we might have.
Finally.
There we go. Yay. All right. First things first. Iteration timer delay. Here we go. Timer delay. 10 seconds. Now let's go back to value noise. I'm going to take this out for now because I just want to return the raw noise and see what we're getting. So, and this one. All right, so now just get raw noise back out. And if I hit play, there we go. All right, so that one, I'm trying to, oh, I know what I was doing. My noise is based off of my other R&D project, the one that you know about, where it's kind of useful to have a lot of black and only a little bit of noise at various spots. So, yeah, we don't want to use the ×2 - 1 in this case. But we're starting to get some smooth noise. We're still taking an incredibly long time to do it. And for the most part, it looks exactly like what we're getting out of our smooth noise.
Yeah, comment out the your noise call and put the hash back in. Well, go ahead and stop the execution here.
Well, I tried.
There it
Still
goes.
waiting.
Yeah, it just takes a few seconds to do. So back over here, I just want to see the difference in time. Obviously, it's going to be significantly faster because you've got, numerous
Well,
smooth noise calls inside of
well,
noise.
we're only doing, yeah, we're doing some lerping and 4 more noise calls. So,
Yeah, it's getting pretty heavy.
yep, this button. All right, so I'm gonna get the mouse working and the keyboard working at some point today.
Okay, so you
But
have 1 second,
yeah,
a
so
little bit over a second and a half.
yeah, about 4 times as much, which is what we expect. But
Yep,
it looks a
almost
lot
identical.
right, which we kind of expect. But here's where the difference comes in. If we go back to code, and if we go back to where our noise was, and we divide our smooth noise by, let's say, well, just to make it obvious, 4F
Hmm.
on both X and Y. So why are you not happy? Oh, smooth noise requires integers. All right. So I can't show it with that one, but well, I could if I do this. We'll lose some precision, but it should still. So what we would want it to do is to scale, but because it's noise still, or based off that hash, remember when we were experimenting in the other video, even when we started changing the scale of our noise,
Hmm.
it still looked like white noise. So even with this, with our smooth noise, we should still end up with white noise. So it should be a high frequency. Well, no, it actually started averaging it out. Nice. So it's starting to smooth out. I thought it was going to end up as starting the like we had before, where it wasn't scaling,
Hmm.
so we still had the high frequency noise.
Hang on, it just didn't catch the
I think
breakup.
it did. Oh, did it?
No, it's all good.
Okay. This is what happens when we're going over a frame. All right, so now it does actually sample, which I didn't think it was going to. So the box splitter is picking it up. What I was hoping for was 4F. All right, so if I build this out, we run this, this should get it even slower.
Hmm.
So we're starting to get it. We're still getting some rough stuff because of the sampling part.
Wait a minute. Did it build? Jump back over your
Uh,
code.
Probably not. No, I built. So it didn't compile.
Yeah, it didn't. It didn't. Yeah, that's what I meant by build. Was it didn't compile over in Unity? It couldn't have because your time was exactly the same and it looked exactly the same. Hang on. Let's see what we get now. That's better.
I can't see anything.
Hang on. There it goes.
Yeah. Okay, so now it's much smoother.
Yes,
Because
it
if you
is.
remember before, it was pixelated. Now this is smoothing. This is doing our interpolation. That's why we're doing the lerps and the smooth. So we're getting, instead of the blocks that you get with just the smooth noise. Now this is using linear interpolation. So if we want to go ahead and do the screenshot of this one,
Okay.
so we can add it in with the other one.
Let me go ahead and see if I can catch stop on it. And there you go.
Okay.
Go back to whichever.
Do you want to paste it in? And
Oh, sure.
it's just easier for you to manipulate images than
Yeah, I understand.
me from here.
Good enough.
All right. Control A. Whoa. No, not Control S. Okay, so Control C. Go back over here. This one. All right. Control Alt C. because we're going to be sampling another one as well. So we'll double up this size.
Here, I'll go ahead and do that part.
Okay.
Just to make it a little easier. All right. Now, did you want to jump back over and...
Yep. Now I want to change up our value noise. And I also want to go back into Firefox. All right. Now, what I want to cover at this point is literally we're doing LERP, or linear interpolation.
Mm-hmm.
Now, if we look at this image here, where we're taking our random points, so we're still taking our random points and we're smoothing those out. That was the second image that we got with the nice smoother noise. But we're in between each of these points, we're not using this nice rounded curving. We're literally just drawing sawtooths from point to point.
Mm-hmm.
We're because that's how linear interpolation goes. It just goes, okay, between these 2 points, draw a straight line. Between these 2 points, draw a straight line. We're not getting this. Now, for our use right now for speed and the outcome, that looks smooth enough for our purposes. If you wanted to do something a little bit closer to this type of curve, we've got two options. We could write our own function. And if we scroll down, down here somewhere, there is a method that they include that allows us to do this type of interpolation. Right here, this cubic interpolation is one method, and there's also a cosine interpolation. We're doing linear. Then you got cosine interpolation. So this kind of shows you what's going on. We're using this method where we're drawing these little sawtooth-like forms,
Mm-hmm.
where cosine interpolation gives you a little bit more rounded. This is almost like ease in, ease out from point to point. And then you've got cubic interpolation, which gives you this nice rounded look. Also is a little bit more complicated. You could use any one of these if you wanted to, if you need that level of fidelity in your curves. Now, if I jump back over here, we could also do something similar without having to write our own methods. We have smooth step that is provided by the mathf functionality. So we could use smooth steps. And I can build this out. And we can run this. So now we're starting to get a little bit more of that noise that's coming back in. It's supposed to be smoothing, but I find that the linear interpolation, gives me better results. So I haven't bothered with any of the other methods. So if you want to copy and paste this out.
Sure.
We didn't incur much of a penalty of about an extra 100 milliseconds.
Let's see if I can catch this first. There we go. And let's go ahead and there you go.
See, I don't need that one anymore. Don't need this one anymore. Yeah, I can see it. I wonder if how visible it'll be on the regular. But if you look closely, this image is a little bit more pixelated than what we were getting with the linear interp.
Mm-hmm.
Which is why I use the linear interp as opposed to the other one. Now, when I was playing with the cosine method,
Mm-hmm.
I got something closer to the smooth step look.
Okay.
And I never really played with the cubic just because of the intensity of the equations on it.
Mm-hmm.
And this is already running slow enough.
Yeah.
So I didn't want to mess with that. Now, the last thing that I want to kind of cover through here is if we go back into code, we're only getting one level of noise here. So if I go back into our game manager and get this set up, I also want to bring this back up, because if we scroll back up, what we are returning is in fact noise. What we're not returning is what most people think is noise. This is noise. Each one of these octaves, as they're called, or iterations through, is noise with a certain frequency and a certain amplitude. Most people, though, associate an image like this as noise as opposed to these. And this is just multiple octaves being rendered at different frequencies and then combined together to give us a noise. And what we've been showing up to now doesn't look anything like this. So what I want to cover is how we can go about doing something like that. And surprisingly, it's not very hard. So if we go back up to here, let's go ahead and put another loop in real quick. So we'll do for I equals, and I'm going to hard code this with a number. And I want to use floats though. I don't want to use integers. And then what I want to do is ensure that our upper limit is going to be what we get out of the function math.power. And I'm going to take the power of 2 and I'm going to raise it to the number of octaves that I want. In this case, I want 8 octaves. I is not going to increment linearly, but exponentially, so it's going to be times equals 2. So every iteration through, I is going to double. And I don't want to start at 1 or 0, I want to start at 1. So if I go up here, we're going to define noise outside of this. So n is going to equal 0. I'm going to take our noise that we're working with. I'm going to copy it. I'm going to paste it inside, comment out this one. So n is going to equal the sum of what was before it, and we're going to divide by I, which is why we made I a float, by the way. And then we're going to need a counter. So var, let's just go count equals 0. Count is going to increment every step through. The reason I need this is n is going to be equal to n divided by count. And I'm going to make count a float. So what we're doing is we're going to iterate through our noise method by the number of octaves that I've defined by power. Each time through, it's effectively going to be cutting our frequency in half. It's going to add that to whatever n was before it. So we're getting the sum of each octave of noise added to each other. I'm keeping track of how many times through we've gone through. I could go ahead and say, 8 specifically, but I want to be able to change this up later. And then I'm taking our total sum and dividing that by the number of times through that we've iterated through our loop, which gives us an average of noise. And then I take that average and assign it to the color that we get. So if I build and we get no errors.
Boy, this is going to be interesting.
Yeah, this is going to be kind of slow.
Yeah.
So, matter of fact, before I even run that, let's go back to here. And I'm not going to increment my timer delay or reset it. because I only want this thing to run once.
Yeah, very good idea.
So if I hit play,
And we kick back and talk about the
relax for a
weather.
little bit. Well, you know what? Almost 7 seconds in iteration. We're doing 8 octaves of noise now, so almost a minute.
Phew.
So
So when we move over to 3D,
yeah, once we get into 3D and this number gets even more intense, and we're only doing a 256 by 256 texture. We're not even doing a really large texture. So I'm just hoping it works. So because if it crashes, I'm not really gonna know. So how long have we been talking now?
oh, in this video, just about to hit 36 minutes.
No, I mean since I hit the play button.
Oh, well, I don't know. Maybe 15, 20 seconds.
Right. So, if we were trying to do this in real time, in
Oh,
between frames, wow. And you thought some of those terrain patches took a while to generate. Could you imagine if we were trying to use this noise to build that height map in real time?
oh, jeez. Yeah, it just wouldn't happen.
Huh. I wonder if it's working still. It
Well,
should have came by now.
you think so? I don't. I think just a little bit longer.
Okay.
I'll start looking at the clock over here just to kind of get an idea. Everyone else can just kind of fast forward.
Yeah.
Or better yet, I'll just hit pause and we'll let it
Okay.
run for a bit longer because I
All right.
I expect this to be a bit on the intense side. Wait, never mind. Yeah, you were pretty close on the.
Yeah, about 1 minute, but we got no results out of it.
Nope.
So that's kind of funny there. There's a dot right there. I wonder what
Ooh.
happened. So I'm going to stop this. I'm going to try to stop it.
Hang on.
I know what happened.
All right, hang on 1 second. Let me go ahead and. Well, go ahead.
Pause.
Switch back over. We'll see if that catches.
Well, we're gonna have to kill Unity because what I screwed up is when I commented out the timer to stop counting.
Mm-hmm.
That means once it goes below 0, it's trying to do this every frame.
Oh yeah, that's bad. Hang on 1 second. Let me go
Yeah.
ahead and pause, and we'll get this sorted then. Okay, Lee, we've resumed.
Yeah, there's a few issues, but the biggest one that was killing us was, our noise is taking in the order of seconds to complete. And we're doing an update inside, or update noise inside of an update, which our update is running, multiple times per second, like 60, 100, 500. And it keeps going into update, or telling it to update noise. But the problem is we're not resetting our timer until after we've done all this other calculation. So we keep getting hung up and we're trying to run it over and over again. So what we're going to do is take our timer and remove that from the end of our operation to the very beginning. So this is going to ensure that we're not going to be firing off our update noise multiple times within the time period. I'm also going to add a couple more zeros up here just to make sure that we don't run any more than once.
Why don't you like keeping that up, like the resetting your timer up, like inside the if timer is less than or equal to 0?
Oh, up here?
Yeah, because that's why I didn't like it to begin with, and as we said off camera, that was my
Well,
big concern. But you've done
you
this,
want to
and
do? Yeah, we can do that. Fine. Yeah, backseat programmer.
I told you I've been quiet, but that one was driving me insane. Now I feel better. Thank you.
Fine. Are you happy now?
I am. Okay.
Okay.
So what else?
Well, the big one is I kind of got backwards when I was originally coding this, and I had set it multiplied by 2 and then subtracted 1f from it to put it in the domain. And I was saying, yeah, this is to put it in the 0 to 1 domain, which I didn't want to do. I forgot how this is working. All my noises are designed to return -1 to +1. And I was thinking backwards, thinking that this was setting the domain to be 0 to 1. That's not true. I need this because I'm taking whatever my value is, which is a 0 to 1 space, multiplying it by 2, then subtracting 1. This is what's actually converting me to be from 0 to 1 to -1 to 1. Because if nxy comes back at 0, I multiply it by 2, that gives me 0, subtract 1 from it, that gives me my -1. If nxy equals 1 times 2 is 2, minus 1 is 1. So this is giving me my -1 to +1 space, which is what all my other noises will be returning. So that's to keep everything consistent. I was getting confused with my hashes and my random number generator being in the 0 to 1 domain. So that was one of the things that I had to adjust and put back here, which means that inside of here, our noise, as this is coming back out, needs to be adjusted to be the 0 to 1. So we need to add 1 to it, and then divide by 2f. So this will convert us back to a 0, 1 space for our noise. Now, a couple of other things is because I'm trying to get accumulation of my count and my noise per iteration, per pixel, having the var n and count outside of my loops is going to blow everything out to white eventually. They have to be reset on a pixel by pixel basis. So every time we go into a new X and Y, these need to be reset. So as we go through each of the iterations, we get the information that we're expecting. So if I go back and drop this down to a single iteration and I build it, so make sure that everything else is the way I expect it to be. Cross my fingers and hope I didn't miss anything.
Now we're also going to see a difference in a big difference in time as well.
Well,
Oh no, we're not. Hang on.
no,
There's
no.
yep.
Yeah, we're still going to see long times, but we're not going to see the these times will be right. We're not seeing the long render times because we're not constantly forcing that update over and over and over again.
Right.
So we're doing one iteration. We're getting the noise that we expect. We're still under just under about 7 seconds or about 6.5 seconds here. So we're still using a 256K texture. But if we go back up and get back to the code.
What code are you getting to? Yours? There we go.
No, I was trying to get the bar to pop up. So if we jump this back up to 8 and we run it again, we're going to be at right about a minute for all 8 octaves. So if I run, now do you want to pause this when I run it, or do you want to just let it run for the minute and we talk?
I'll go ahead and pause real quick just to save them from having to wait. Here we go.
Okay.
Okay, so we're unpaused. 52 seconds.
Yep, and 177 milliseconds. But as you can see, we've got something that looks closer to what people expect when you say noise. We've got some larger patches of discoloration, like in this area where it's a darker gray, this little outline that's a lighter gray. So it's got some low frequency splotchy areas with some higher frequency as we go down until we get this really higher or high frequency noise, which just kind of looks like speckles all over the place, which you might not be able to see quite as well on the video encoding. But it is there, and it is soft. It's not the really harsh white noise that we get with the regular
we could
regular
don't hit stop.
noise.
We could go ahead and screenshot this, put it at the end
Go
of the
ahead.
other one, so that we can, as we
Compare
get into other noises, we could also compare as well.
Right.
All right, let me go ahead and get this guy captured. Wow, being a little sluggish on me.
Well, we are still running.
And that would be a good reason why.
You're recording, running Unity, and copying and pasting all in Photoshop.
I love my new computer. All right, there you go.
Yeah, your old one would have blown up several times by now.
Oh, goodness, I know. So glad we did upgrade. Wait, you're going to go down with it?
Yep.
Okay, we can adjust it later. I was thinking if you were going to keep these all running across, then we could have done like the next row as the next kind of. But that's good. Paste.
Well,
Paste.
I was going to try to keep it over. No, it's all right. It's
No,
fine.
no, just paste, paste. It's all good. We can do that
No,
stuff off. Oh, Lee.
I'm gonna do it my way. No, it's not hard, but yeah, I see what you're saying. So instead, we need to add. Okay, so divided by
You
4,
could have just
that's
done
roughly
done and
256. What's that?
nothing.
I could have done something.
That's good. Yeah, very nice seeing it up against all of the other ones. Big, big difference.
Now, if we just would have copied all the times underneath it.
True. But still, we can at least look at the different.
Right. Because basically, this is our white noise from our hash. This is our box blurred soft noise or smooth noise.
Hang on, let me go ahead and zoom in at least. Well, I mean, if we did 2, and so we're up at 100%, that would. So now you can just do this right here. So it's easier to see what's going, especially with the little bit of blurring in here when you're
Right.
zoomed in a bit closer. So continue.
But then we've got our box blur. This was some experimentations with just the smooth noise using the LERP or linear interpolation and the smooth step interpolation. And then this was 8 octaves of noise put together, but runs at almost a full minute to get just a single 256 by 256 texture. And I want to jump back and see if I'm still using the smooth step. Yeah, I am. So if I'm still using the smooth step on that. So we can change that back to LERP as well. But the cool thing is you can see where we start losing, back to Photoshop, we can start losing once we do the octaves. We don't pick up the pixelation. And also, to be fair, these were captured at 128 by 128 as opposed to the full 256. So that's why they look a little bit, or no, we did the divide by 4 on both of these.
Gotcha.
Where we're using octaves, we are still dividing, but because we're blending those all together and averaging them out, we don't see any of the stepping whatsoever. And what we end up with, yeah, I'm trying to scroll, it's not working well. But we end up with that nice smooth looking noise that everybody expects when you start generating noise. So what this is the equivalent of this guy right down here with all the octaves applied with decreasing frequency each iteration through or each octave through.
Okay.
So that is what I wanted to show with our 2D noise. Now, we're going to do the same thing with 3D noise. Now, we're going to run into a problem. We've already kind of hit on the fact that a 256 by 256 texture with 8 octaves of noise on it takes a minute to update. Our 3D noise, the big advantage that we're going to get is we can iterate across the Z component to animate our noise. But with it taking a minute a frame, we're not going to really see that very well. So we're probably going to end up having to knock down the number of octaves a bit and probably downsize the overall image so we can actually see it in action.
Exactly.
But that will be the stuff that we'll tackle in the next video.
All right, fantastic. Well, with that, we will go ahead and wrap up this video. Thanks a lot, everyone.